Every story we have ever told, from the whispered myths of our ancestors to the grandest epics of our creation, shares one immutable feature: an ending. We are creatures defined by narrative, obsessed with the final page, the closing credits, the ultimate fate of our heroes and our worlds. It is a deeply human instinct, this need for closure. So it is only natural that when we cast our gaze outward to the grandest story of them all, the story that contains every other, we ask the same profound and perhaps unsettling question: how does the universe end? For generations of thinkers, stargazers, and scientists, the answer seemed to be a choice between two powerful, almost poetic destinies. Two final acts in the cosmic drama. The first was an ending of fire, a magnificent and violent homecoming. The Big Crunch. In this scenario, the universe was like a stone thrown into the air. The initial explosive energy of the Big Bang would eventually be overcome by the relentless collective pull of gravity. Every galaxy, every star, every fleck of dust bound together by this invisible cosmic leash would one day cease its outward flight. The expansion would slow halt and then inexorably reverse. Galaxies, once fleeing from each other across billions of light years, would begin a slow, majestic convergence. Distant points of light in our telescopes would cease to be redshifted and begin to glow with an ever-intensifying blue, their journey homeward accelerating. Imagine that far future sky, a canvas no longer dominated by cold, empty blackness, but increasingly crowded with the fiery jewels of approaching galactic islands. Over eons, these islands would merge in cataclysmic collisions of stars and gas, not as destroyers but as tributaries flowing into a single roaring river of light. This river would become a sea and then an ocean of plasma as the universe compressed heating to unimaginable temperatures. Stars would dissolve, planets would vaporize. The very atoms that once formed our world, our bodies would be stripped of their electrons in a celestial furnace. All of existence would be crushed back into a space smaller than a single proton, a gravitational singularity of infinite density and heat, a final incandescent point. And yet, for all its violence, there was a kind of comfort in this theory, a sense of symmetry, a cosmic cycle. From a singularity the universe was born, and to a singularity it would return. Perhaps some whispered it would even be reborn, a cosmic phoenix rising from its own ashes in another Big Bang, another universe with another chance at life. The end was not just an end, it was a prelude, a punctuation mark before the next grand sentence. The alternative was a quieter, more melancholy fate, a story not of fire but of ice, the Big Freeze. In this telling, gravity was not strong enough to halt the universe's expansion. The stone thrown in the air would never fall back down. It would simply keep flying, forever slowing but never stopping. Galaxies would continue to drift apart their light, stretching, reddening, and eventually fading beyond the horizon of our perception. The sky, once full of neighbors, would become an increasingly desolate and lonely place. One by one, the other galaxies would wink out, leaving our own Milky Way, an isolated island in an endless, unbreachable void. But the fading was only just beginning. Within our own galaxy, the great stellar nurseries would run out of gas. Star formation, the engine of cosmic light and life, would cease. The universe would have created its final generation of suns. The existing stars, from the brilliant blue giants to our own placid yellow sun, would exhaust their fuel over trillions upon trillions of years. They would swell into red giants, then collapse into the cold, dense embers of white dwarfs, neutron stars, and black holes. The universe would enter its stellar twilight, a deep and profound darkness punctuated only by the faint, dying glow of these cosmic corpses. Even these would eventually cool, radiating away their last vestiges of heat, until they became invisible frozen husks of black iron adrift in an eternal night. The age of light would be over. The very last dregs of energy would be consumed, leaving a universe of unimaginable cold and emptiness. A silent, sprawling graveyard of matter where the temperature approached absolute zero and the arrow of time itself might lose all meaning. It was a somber, lonely vision, the heat death of the universe. Yet like the Big Crunch, it had a certain finality, a grim elegance. It was an ending we could comprehend, a slow fade to black, a final peaceful winter after a long and brilliant summer. For most of the 20th century, these were our choices. a spectacular fiery death or a long cold goodbye. The cosmos would either close with a bang or with a whimper. The debate was fierce, the calculations complex, but the fundamental options seemed clear. Humanity, in its quest to understand its place in the universe, had at least sketched out the final chapter. We believed we were living in the story, and while we didn't know the precise ending, we felt we knew the genre. It would be a tragedy, perhaps, or a grand cosmic epic with a cyclical mythic structure. We were wrong. We were devastatingly, terrifyingly wrong. We had failed to account for a ghost in the cosmic machine, a force so strange, so powerful, and so utterly counterintuitive that its discovery didn't just add a new ending to the story. It threatened to rip the very pages the story was written on to shreds. The revelation began, as so many do, not with a sudden flash of insight, but with the patient, meticulous act of observation. In the late 1990 seconds, teams of astronomers were engaged in one of the most ambitious projects in the history of science to measure the precise rate at which the universe's expansion was slowing down. They were trying to weigh the entire cosmos to finally determine whether we were destined for fire or for ice. To do this, they used a special kind of cosmic lamppost, a specific type of exploding star known as a type Ia supernova. These stellar cataclysms are what we call standard candles. Because they are all triggered at a very precise mass, they erupt with a near-identical predictable brightness. By measuring how faint a distant supernova appears, astronomers can calculate its distance with astonishing accuracy. By measuring its redshift, they can determine how fast it and its host galaxy are moving away from us. They pointed their most powerful telescopes to the deepest, most ancient reaches of the cosmos, hunting for these fleeting, ghostly explosions. The plan was simple. Look at the most distant supernovae, which are also the oldest, and compare their speed to that of newer, closer ones. This would create a history of cosmic expansion. Everyone knew what they would find. They would find that the expansion was faster in the past and is slower today. The only question was how much times slower. Was it slowing enough to eventually reverse into a big crunch, or just slowing enough to coast forever into a big freeze? One by one, the data points came in, and they made no sense. The numbers were backward. The readings seemed impossible, a glitch in the equipment, a flaw in the calculations, a fundamental misunderstanding of the physics. The most distant supernovae, the ancient ones from the youth of the universe, were not brighter than expected. They were fainter, significantly fainter. The only way this could be true was if they were farther away than their redshift predicted. And the only way times could be true was if the space between them and us had stretched more than anyone had dreamed. The universe's expansion wasn't slowing down. For the past 6 billion years, it had been doing the exact opposite. It was accelerating. It was a discovery that shook the foundations of cosmology. It was like throwing a stone into the air and watching it against all logic and all laws of gravity we held dear suddenly shoot upward faster and faster into the sky. Something was pushing the universe apart. Something was acting as a cosmic anti-gravity, a mysterious pressure inherent in the fabric of space itself, overwhelming the collective pull of all the matter and energy we can see. We couldn't detect it. We couldn't measure it directly. We had no idea what it was. So we gave this profound ignorance a name. We called it dark energy. And in the shadow of this discovery, a new and far more violent endgame began to creep into the minds of theoretical physicists. A third option, one that made the fiery furnace of the crunch and the endless winter of the freeze seem like gentle mercies. This new hypothesis began with a simple, terrifying question. What if dark energy is not constant? What if this mysterious, repulsive force is not just a gentle, persistent push, but a force that is growing stronger over time? Scientists gave a name to this even more exotic form of energy, phantom energy. And if it exists, it leads to a fate so absolute, so comprehensively destructive, that it has been given a name worthy of its horror, the Big Rip. It is not an ending, it is an annihilation. A complete and utter unraveling of the tapestry of existence from the largest cosmic structures down to the innermost sanctum of the atom itself. The Big Rip doesn't just promise a final state of darkness or heat. It promises a final, fleeting moment of incomprehensible violence that will tear apart the very meaning of structure of form of being. In the final act of this scenario, the accelerating expansion driven by this phantom energy becomes so powerful that it will in turn overcome every fundamental force of nature. Let us paint a picture of this final timeline, a countdown to oblivion. For billions of years, the process would be subtle. Galaxies would continue to fly apart much as they do now, only faster. But then, as the power of dark energy continues to mount, a terrible new phase would begin. Roughly 60 million years before the end, the repulsive force of space-time itself would become strong enough to overcome the gravity that binds galaxies into clusters. Great cosmic families of galaxies like our own local group would be unbound, its members flung into the expanding void, each one set on a course for total isolation. Then, the focus of the destruction would narrow. Around 20 million years before the final moment, the dark energy density would grow so immense that it would overwhelm the gravitational pull that holds individual galaxies together. For the Milky Way, it would be a slow, majestic, and horrifying disintegration. The great sweeping spiral arms, those beautiful rivers of stars and gas, would be torn from the central hub. The galaxy would unspool like a ball of yarn, its billions of stars cast adrift into the terrifying expanding darkness. The night sky of any remaining world would fill with the sight of its own suns being flung away, becoming lonely, solitary wanderers. Just 3 months before the end, the destruction would arrive at our doorstep. The phantom energy would become powerful enough to overcome the gravity of our own Sunday. The solar system, that stable clockwork model of gravitational harmony, would be shattered. Jupiter, Saturn, and the outer worlds would be the first to go, their orbits broken their paths, sending them careening into the void. Then Mercury, Venus, Mars, and finally the Earth itself would be ripped from their celestial anchor. Our planet would become a rogue world, untethered, tumbling alone through the rapidly dissolving tatters of its former galaxy. The final hour would be one of unimaginable chaos. The Earth itself, no longer held together by the Sun's gravity, might not even survive as a cohesive sphere. But it wouldn't matter, because minutes before the end, the swelling power of dark energy would become stronger than the electromagnetic forces that bind atoms and molecules together. The very ground beneath our feet, the oceans, the atmosphere, every structure we have ever built, every living thing would lose its integrity. The chemical bonds would snap. Matter itself would dissociate into a hot plasma of unbound atoms. The planet would simply evaporate. But this is not the end. The Big Rip is more fundamental, more absolute. In the final femtoseconds, the repulsive force of space-time would become infinitely strong. It would overcome the strong nuclear force, the most powerful force in nature, the cosmic glue that holds the nuclei of atoms together. Protons and neutrons would be torn apart into a quark gluon plasma. And then in a moment so brief it defies description, space-time itself would be ripped asunder. The very fabric of reality, the stage upon which the entire cosmic drama has played out, would be shredded. Every particle, every quantum field, every law of physics as we know it would cease to exist. The end would not be cold, darkness, or hot density. It would be the end of distance, the end of time, the end of all physical law, an infinitely expanding void of absolutely nothing. The ultimate erasure. This isn't just a theory about the end of stars and planets. It is a theory about the end of information. Every work of art, every scientific discovery, every act of love, every memory, every trace that we ever existed would be obliterated not just in practice but in principle. There would be no cosmic embers, no dying light, no collapsed singularity containing the seeds of a new universe. There would be only the void, a universe torn so completely apart that it ceases to be a universe at all. So this is the cosmic mystery we now face. We have peered into the darkness between galaxies and found a force that is pushing everything apart. A force that accounts for nearly 70% of all the energy in the cosmos, and yet remains a complete and total enigma. Is this dark energy a simple, unchanging cosmological constant, as Einstein first proposed a gentle pressure that will lead us to a lonely but peaceful heat death? Or is it something more sinister? Is it a phantom, a growing power, an engine of destruction that is even now gathering strength for a final, cataclysmic act of cosmic violence? To answer this question, to determine our ultimate fate, we must embark on a journey. We must probe the nature of this darkness to understand its origins, its properties, and its terrifying potential. We must chase the echoes of the Big Bang map, the largest structures in the universe, and stare into the hearts of dying stars. We are locked in a cosmic detective story searching for clues to the identity of a force that could either allow the universe to fade away gracefully, or one that is destined to tear every single one of us and the very reality we inhabit, atom from atom. The stakes could not be higher, for we are not just asking how the story ends, we are asking if the final word is to be written, or if the book itself is to be ripped to pieces. For all of human history, two fundamental questions have haunted our quietest moments, whispered from generation to generation in the flickering light of campfires and in the sterile hum of laboratories. Where did we come from, and where are we all going? The first question, that of our origin, has found its answer in the blinding flash of the Big Bang, a moment of creation from which all of space, all of time, and all of us emerged. But the second question, the one that speaks to our ultimate fate, remains shrouded in a profound and unsettling mystery. It's a question not just about the end of our world, but about the end of everything, the end of stars, of galaxies, of matter itself. Does the universe, this grand and sprawling stage upon which our ephemeral lives play out, have a final act? And if it does, what does that final curtain call look like? Is it a symphony that ends in a sudden crashing crescendo, or one that simply fades note by note into an eternal, unbreakable silence? By the twilight of the 20th century, we thought we were on the verge of knowing. The greatest minds in cosmology had surveyed the heavens, armed with titanic telescopes and elegant equations, and had narrowed the future down to two starkly different destinies, two epic, opposing narratives for the end of time. This grand cosmic dichotomy was not a matter of philosophy or faith, but of physics. It all hinged on a titanic struggle, a celestial war that has been raging silently across the cosmos for 13.8 billion years. On one side, you have the initial explosive momentum of the Big Bang, the primordial kick that sent every galaxy flying away from every other galaxy, stretching the very fabric of space-time. On the other side, you have the quiet, relentless, and inescapable grip of gravity. Gravity, the force that binds worlds to stars and stars to galaxies, was acting as a cosmic brake, a celestial anchor trying to pull everything back together. The entire future of reality, from the smallest atom to the largest supercluster, depended on a single crucial question: which of these two colossal forces would ultimately win? To find the answer, astronomers believed they had to do something. That sounds deceptively simple. They had to weigh the universe. They needed to determine its total density, the sum of all the matter and energy packed into the cosmos. If the universe was dense enough, if it contained enough stuff, enough stars, gas, dust, and the unseen halos of dark matter that we knew were lurking in the shadows, then gravity would have the upper hand. In this scenario, the expansion that began with the Big Bang would not continue forever. Slowly, imperceptibly at first, but with inexorable certainty, the outward flight of the galaxies would falter. The cosmic brake would grip harder and harder. Across billions of years, the great cosmic expansion would slow to a halt, pausing for a final, magnificent moment of equilibrium. And then the universe would begin to fall. This was the fate known as the Big Crunch. It was a vision of cosmic recoil, a universe collapsing back in on itself. Galaxies which had been racing apart for eons would reverse course, their distant light shifting from red to an ominous approaching blue. The cosmic microwave background, the faint, cold afterglow of creation, would heat up, its gentle hum rising to a roar as it was compressed. Space itself would shrink. Clusters of galaxies would merge not in gentle dances, but in violent cataclysmic collisions. As the universe became smaller, it would become unimaginably hot and dense. The sky would become a solid wall of fire brighter than 1 trillion suns. Stars would be torn apart, their constituent atoms stripped of their electrons. The laws of physics as we know them would break down in a final fiery singularity, a mirror image of the Big Bang, a cosmic Götterdämmerung. It was a terrifying yet strangely symmetrical destiny. A universe born from a single point would return to a single point, perhaps to be reborn in an endless cycle of cosmic death and rebirth. It was a story with a definitive, dramatic, and violent end. But what if the universe wasn't heavy enough? What if all the galaxies, all the gas, all the dark matter simply didn't have enough collective gravitational pull to overcome the primordial momentum of the Big Bang? In that case, we were facing a very different kind of ending. A far quieter, colder, and perhaps more lonely fate. This was the big freeze or the heat death of the universe. In this scenario, gravity would fight a losing battle forever. The expansion would continue, never stopping though. It would slow down over unimaginable timescales. Galaxies would sail ever further apart, their lights stretching and dimming until they eventually vanished over the cosmic horizon, leaving our own Milky Way, an isolated island, in an endless, unbridgeable void. The universe would grow darker. The fuel for star formation would eventually run out. The great stellar nurseries would go quiet, their lights extinguished one by one. The stars that remained would burn through their life cycles, the last red dwarfs finally sputtering out after trillions of years, leaving behind only the cold, dark corpses of stellar evolution, black dwarfs, neutron stars, and black holes. The universe would become a silent, ghostly graveyard populated only by these dead remnants and scattered, aimless particles. Even these would eventually decay. Protons might dissolve over timescales so vast they make the current age of the universe seem like a fleeting instant. The great black holes themselves would slowly, painstakingly evaporate through a process known as Hawking radiation, leaking their energy back into the void until they too vanished in a final, faint puff of particles. What would be left is a universe of almost perfect emptiness. A cold, thin, featureless soup of stray photons, neutrinos, and other fundamental particles adrift in an ever-expanding darkness. A state of maximum entropy from which no useful work could ever be extracted. A reality without structure, without warmth, without life, without memory. A story that doesn't so much end as it simply stops. It was a vision of cosmic oblivion, a slow fade into nothingness that stretched into a chilling eternity. So, there it was. The battlefield of late 20th century cosmology was defined by these two epic possibilities: a fiery death in the Big Crunch, or a slow frozen demise in the Big Freeze, fire or ice, collapse or decay. The choice between them was a cosmic cliffhanger, and the scientific community was galvanized in its quest for an answer. The challenge was immense. How could you possibly put the entire universe on a scale? The key, they realized, was to look deep into the past. Because light travels at a finite speed, looking at distant galaxies is like looking back in time. If you could precisely measure the distances to galaxies at various points in cosmic history, and also measure the speed at which they were moving away from us, you could build a history of the cosmic expansion. You could see for yourself whether the universe was in fact slowing down, as gravity intended. You could measure the rate times of deceleration. Finding that one number would tell us everything. It would reveal the density of the cosmos and with it, our ultimate destiny. But measuring cosmic distances is one of the most difficult tasks in all of science. You need a standard candle, a celestial object with a known, consistent brightness. Imagine seeing a streetlight in the fog. If you know exactly how bright that streetlight is supposed to be, you can tell how far away it is just by seeing how dim it appears. Astronomers needed the cosmic equivalent of that streetlight, something so brilliantly luminous it could be seen billions of light years away, and so reliable that its intrinsic brightness was always the same. They found it in one of the most violent and spectacular events the universe has to offer, a Type Ia supernova. This specific kind of stellar explosion occurs when a white dwarf, the dense remnant of a sun-like star, siphons material from a companion star. As it greedily pulls in more and more matter, it eventually reaches a precise critical mass, about 1.4 times the mass of our Sun. At this exact tipping point, known as the Chandrasekhar limit, it can no longer support its own weight, and it ignites in a cataclysmic thermonuclear explosion. Because every single Type Ia supernova is triggered at this exact same mass, the brightness of the explosion is incredibly consistent. They are astonishingly powerful cosmic lighthouses. For a few weeks, a single one of these exploding stars can outshine its entire host galaxy, a blazing beacon visible across billions of light years. They were the perfect tool. If you could find these supernovae in the distant universe, and measure their apparent dimness, you could calculate their distance with unprecedented accuracy. By comparing that distance to the redshift of their light, the amount their light has been stretched by the expansion of space, which tells us their recession speed, you could chart the history of cosmic expansion. You could finally definitively measure the rate at which gravity was slowing everything down. Two competing teams of brilliant astronomers, armed with the world's most powerful telescopes, set out to do just that. On one side was the Supernova Cosmology Project, led by Saul Perlmutter. On the other, the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees. It was a race to discover the fate of the universe. The expectation was clear. Everyone knew the universe had to be decelerating. Gravity was the undisputed master of the cosmos on large scales. The only question was how much times it was decelerating. If the supernovae they found were relatively bright, it would mean they were closer than their redshift would suggest. This would indicate that the expansion had slowed down significantly over time, a sign of a high-density universe heading for a big crunch. If the supernovae were dimmer, it would mean they were farther away than expected, indicating the expansion had not slowed down as much. This would point to a low-density universe, one destined for a long, cold, big freeze. They pointed their telescopes to the heavens, hunting for these faint, fleeting explosions in the deepest, most ancient corners of space. It was painstaking, meticulous work requiring years of observation and incredibly complex analysis. They found their supernovae, dozens of them scattered across cosmic history. And then, as the data began to pour in, something utterly impossible began to emerge. Something so wrong, so contrary to all expectations, that the scientists on both teams initially assumed their equipment was faulty, their calculations were flawed, or that they were being fooled by some unknown cosmic dust. The supernovae were not brighter than expected, nor were they just a little bit dimmer. They were significantly, undeniably, inexplicably dimmer times than they should have been in any possible model of a decelerating universe. The only way for them to appear this faint was if they were much, much farther away from us than anyone had ever imagined. And the only way for them to be that far away was if the expansion of the universe hadn't been slowing down at all. The data was screaming a conclusion so radical it bordered on cosmological heresy. Sometime in the last several billion years, the expansion of the universe had stopped slowing down and had started to times speed up asterisk. The universe was accelerating. Imagine the shock. It was as if you threw a set of keys up into the air, expecting gravity to pull them back down, but instead they shot upwards faster and faster, rocketing away into the sky. It violated everything we thought we knew about the cosmic struggle. Gravity wasn't winning. It was losing, and losing badly. The initial momentum from the Big Bang wasn't the only thing driving the galaxies apart. Something else was out there. Something was pushing. A mysterious, invisible, all-pervading energy was acting as a form of cosmic anti-gravity, actively forcing space-time to expand at an ever-increasing rate. The two teams checked and rechecked their findings, terrified of making a career-ending mistake, but the data was relentless. The evidence was irrefutable. In 1998, they stood before the world and announced their groundbreaking Nobel Prize-winning discovery. The fate of our universe was not a simple choice between fire and ice. A new, unknown character had just walked onto the stage, and it was completely rewriting the final act. They gave this mysterious entity a name, a label, that perfectly encapsulates both its profound importance and our profound ignorance of its true nature. They called it dark energy. It is not dark in the sense of being black. It is dark in the sense of being utterly unknown. It doesn't seem to interact with light or matter in any familiar way. It is a ghost in the cosmic machine, a phantom pressure inherent to the vacuum of space itself. Albert Einstein had once theorized about such a force, a cosmological constant he added to his equations to create a static universe, a fudge factor he later called his biggest blunder. But here it was seemingly real, resurrected from the ash heap of history to explain this astonishing acceleration. This discovery didn't just add a new possibility to our cosmic destiny, It shattered the old framework entirely. The old debate between the Big Crunch and the Big Freeze was suddenly rendered obsolete, a relic of a simpler time. We now understood that we live in a universe dominated not by the familiar matter of stars and galaxies, nor even by the enigmatic pull of dark matter, but by this strange, repulsive dark energy. It makes up nearly 70% of the total energy density of the cosmos, and its influence is growing. As space expands, the density of matter and dark matter thins out their gravitational grip, weakening over cosmic distances. But the density of dark energy bizarrely appears to remain constant. It doesn't dilute as space expands. This means that as time goes on, its repulsive force becomes more and more dominant. The acceleration we are witnessing today is only the beginning. This revelation opened a Pandora's box of new, terrifying questions. What times this dark energy? Is it the energy of empty space, Einstein's cosmological constant? Or is it something even stranger, a dynamic field that could change in strength over time, a quintessence? And most chillingly of all, if this acceleration continues to grow, what does that mean for the future? What happens when a runaway force that pushes space apart becomes the undisputed ruler of the universe? The discovery of dark energy solved the old mystery of our fate, only to replace it with a new one far more violent and profound than we had ever dared to imagine. It set us on a new path, a frantic quest to understand this cosmic phantom before it unravels the very fabric of existence, leading us toward a final destiny not of fire or ice but of something else entirely. An end known as the Big Rip. With the initial shockwaves of discovery beginning to settle, an even more profound question settled over the world of cosmology. It was no longer enough to know that some invisible energy was driving the cosmos apart. That was the headline, the astonishing fact that had overturned a century of thinking. But for the scientists on the front lines, the real work, the truly daunting task was just beginning. They had to move beyond the mere existence of dark energy and begin to understand its character, its personality. They had to write its biography. To know your enemy, you must know its nature. Is this force a constant, a simple cosmological background hum that has been there since the beginning, or is it something more dynamic, a presence that changes, that evolves, that perhaps even grows stronger with time? The answer, buried in the fabric of space-time, would determine the ultimate fate of everything you have ever known. It would be the difference between a slow, quiet fade to black and a final, unimaginably violent crescendo. So began one of the most ambitious forensic investigations in the history of science. The crime scene was the entire observable universe, and the clues were written in the most ancient light and the grandest structures imaginable. The first piece of evidence lay in the afterglow of creation itself, the cosmic microwave background radiation. We've come to see this as the universe's baby picture, a snapshot from just 3,800,000 years after the Big Bang. But it is so much more than a picture. It is a blueprint, a diagnostic chart containing the precise initial conditions of our cosmos. Etched into that faint, persistent glow are tiny, almost imperceptible variations in temperature. These are the fossilized echoes of quantum fluctuations from the first moments of time, magnified by inflation, into the seeds of all future structure. They are the starting point for every galaxy, every star, and every planet. By studying the size and distribution of these primordial hotspots and cold spots, we can determine the fundamental geometry of the universe. Think of the fabric of space-time as a vast cosmic drumskin. The patterns of vibration, the tones it produces tell you exactly what it's made of and how tightly it's stretched. The cosmic microwave background is the sound of that drum ringing across 13.8 billion years. Dark energy acts as a lens, subtly distorting the path of this ancient light as it travels towards us. The presence of this repulsive force changes the apparent size of those ancient patterns. By measuring them with breathtaking precision, using probes like the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck satellite, we could infer just how much dark energy was woven into the cosmic fabric. The data confirmed its existence with undeniable authority. It was not a fluke. It was a dominant component of reality, accounting for nearly 70% of the total energy budget of the universe. The second line of inquiry was written on a scale that defies human comprehension. Look out into the cosmos, and you will see that galaxies are not scattered randomly like dust motes in a sunbeam. They are organized. Gravity, the great sculptor, has spent billions of years pulling matter together into magnificent, intricate patterns. It has spun luminous filaments of galaxies, stretching for hundreds of millions of light years, surrounding vast, dark voids of near-perfect emptiness. This is the cosmic web, the large-scale structure of the universe, and within this celestial architecture lies a detailed record of the epic battle between gravity and dark energy. Gravity relentlessly tries to pull things together to make the rich richer and the voids emptier. Dark energy, its eternal adversary, pushes everything apart, seeking to smooth out the universe and erase all structure. The final shape of the cosmic web is the result of this cosmic tug-of-war played out over eons. By mapping the positions of millions of galaxies, by studying how they cluster together, we can measure the history of that struggle. If dark energy were weaker in the past, gravity would have had an easier time building massive galactic clusters. If dark energy was always strong, it would have suppressed that growth, leaving a more diffuse, less clumpy universe in its wake. These galactic surveys, like the Sloan Digital Sky Survey, became a second independent witness. And their testimony was clear. A powerful, repulsive force was not just active today, but had been shaping the destiny of the cosmos for the last several billion years. Its influence was undeniable, etched into the very placement of the galaxies themselves. But while the CMB and the cosmic web could confirm times that times dark energy existed and times how much times of it there was, they were less adept at revealing its intimate nature. For that, we had to return to the original messengers, the celestial beacons that first alerted us to the cosmic acceleration. We had to return to the Type Ia supernovae. These thermonuclear detonations of white dwarf stars were our standard candles, our cosmic lighthouses. Because they all explode with nearly the exact same intrinsic brightness, we can use them to measure distance with incredible accuracy. They were the tools that revealed the acceleration, but now they would be honed into instruments of unprecedented precision. The goal was no longer just to see if the universe was speeding up, but to measure the times, rate of change times of that acceleration over cosmic time. This required a painstaking, almost fanatical effort. Astronomers scanned the heavens night after night, searching for these fleeting, brilliant flashes in distant galaxies. Each new supernova was a data point, a pin on the map of cosmic history. A supernova that exploded 6 billion years ago told us how fast the universe was expanding 6 billion years ago. One that exploded 10 billion years ago gave us a snapshot from an even earlier epoch. By collecting hundreds of these cosmic mile markers spanning a vast range of distances and times, scientists could begin to plot with excruciating detail the expansion history of the universe. They could see the moment roughly 5 billion years ago when the universe switched gears. They could pinpoint the epoch when the gravitational pull of matter finally lost its dominance and the relentless outward push of dark energy took control of the cosmos for good. Now, with this wealth of high-precision data from 3 independent sources, the time had come to ask the ultimate question. What times is this stuff? How does it behave? Physics needed a way to classify it, to pin it down with a number. That number, a single letter in the Greek alphabet, would become the most important and terrifying variable in all of cosmology. It is called the equation of state parameter, represented simply by the letter W. This parameter is a measure of dark energy's character. It is the ratio of its pressure to its energy density. It sounds abstract, but it is everything. It is the key that unlocks the future. Let's try to make this tangible. For normal matter like the stars and gas that fill the universe, the pressure is effectively 0 compared to its energy. So for matter, W is equal to 0. For radiation, like the photons that make up the cosmic microwave background, there is an outward pressure. For radiation, 1 equals positive 1/3. These are familiar, well-behaved components of our universe. But for an energy field to cause cosmic acceleration to create a repulsive gravity, it must have a negative pressure. It must have a W that is less than 0. Think of it not as a push, but as a tension. a stress embedded in the vacuum of space itself that pulls space-time apart. The simplest, most elegant candidate for dark energy was an idea that had been lingering in the background for nearly a century. It was Albert Einstein's cosmological constant. In his model, the energy of the vacuum was a fundamental, unchanging property of the universe. As space expanded, the density of this vacuum energy remained exactly the same. More space meant proportionally more vacuum energy, a perfect feedback loop driving a smooth, constant rate of acceleration. If dark energy was the cosmological constant, its equation of state parameter would have a very specific value. It would be precisely exactly -1, no more, no less. This was the benchmark. The universe would expand forever, growing colder and emptier until the last stars burned out in a distant, lonely future. A big freeze, a quiet, peaceful end. This became the standard model, the consensus view. But science is not about consensus, it is about doubt. It is about pushing the data to its breaking point to see if it reveals a crack in our understanding. And as the telescopes grew larger, the surveys more comprehensive, and the analysis more sophisticated, the data began to whisper something unsettling. The teams studying the supernovae, the experts analysing the intricate patterns in the CMB from the Planck satellite, the astronomers mapping the cosmic web, their results began to converge on a single terrifying point. When they combined all their data, the best fit value for W was not landing squarely on -1. It was close, but it was consistently, stubbornly hinting at a value that was just slightly less, perhaps -1.03 or -1.05. The error bars were still large enough that -1 remained a possibility, but the hint was there. A crack was beginning to show. A door was creaking open into a realm of physics that no one had ever anticipated. What would it mean for the universe if were truly less than -1? It seems like a trivial distinction, a footnote in a cosmic equation. It is anything but. It represents a fundamental departure from everything we thought we knew about energy. If EBU is exactly -1, the cosmological constant, then dark energy's density is constant. It is stable, predictable. But if is even a fraction less than -1, the situation changes completely. It means that as the universe expands, the energy density of this mysterious force does not stay the same. It times increases *. Let that sink in. As the volume of space grows, the total amount of this energy grows even faster. It's not just that new energy is appearing to fill the new space. It's that the energy in every single cubic centimeter of space, everywhere in the universe, is actively, relentlessly growing more intense. The vacuum is not just simmering, it's beginning to boil. This is not the cosmological constant. This is something else entirely. A new name was needed for this theoretical beast, a name that captured its truly bizarre and aggressive nature. They called it phantom energy. An energy field that feeds on the expansion it creates. A force that grows stronger as the universe gets bigger, creating a runaway feedback loop of terrifying power. The existence of phantom energy would mean that the cosmic acceleration we observe today is not constant. It is in fact the beginning of a hyperacceleration. The rate of expansion is not just increasing, the rate of the increase is itself increasing. It is an exponential spiral into oblivion. Suddenly, the refined academic quest to measure a single cosmological parameter had become a matter of ultimate survival. The data was no longer just describing the past, it was pointing a trembling finger towards a future so violent it strains the very limits of imagination. The gentle, eternal expansion of the Big Freeze was being replaced by a far more horrific possibility. The evidence, still tentative but growing more insistent with each new supernova catalogued, each new patch of sky mapped, suggested that dark energy was not a placid constant feature of our universe. It was a cosmic character flaw, a hidden instability in the fabric of reality itself. And if this phantom energy is real, if U is truly less than -1, then the fate of the cosmos is not to fade away, it is to be torn apart. We had discovered the potential mechanism for the ultimate cosmic cataclysm. The weapon had been identified. The stage was now set for the final act of the universe, a destructive crescendo known with chilling simplicity as the Big Rip. For a time, the elegant chill of the cosmological constant offered a strange sort of comfort. We had stared into the abyss of an ever-accelerating universe and found a kind of predictable, if lonely, end. An eternity of expansion, yes, but a gentle one. A future where the cosmos would stretch and cool its embers, fading into a quiet frozen darkness over trillions upon trillions of years. In this vision, the fundamental laws of physics held firm, a final, unbreakable promise. The universe would end not with a bang or even a whimper, but with an impossibly slow, dignified sigh. This was the consensus, the safe harbor in the storm of cosmic uncertainty. But science rarely rests in safe harbors for long. On the wild frontiers of theoretical cosmology, a far more unsettling question began to stir, a whisper that threatened to turn the gentle sigh into a final, deafening scream. The question was born from a single, deceptively simple parameter in our equations, the letter W. For the serene, predictable big freeze had to equal -1 precisely, not -0.99, not -1.01. It had to be perfect. Yet what if it wasn't? What if nature had no obligation to mathematical elegance? In 2003, three physicists, Robert Caldwell, Mark Kamionkowski and Nevin Weinberg, dared to push that parameter past its breaking point. They peered into the mathematical abyss just beyond that perfect -1 and asked a truly terrifying question: what happens if W is times less times than -1? What they found was not a subtle variation on an old theme. It was a monster. A new cosmology, a new destiny, written in the language of an idea so profoundly strange it seemed to violate common sense phantom energy. They had uncovered a hidden clause in the cosmic contract, an apocalyptic loophole that leads not to a slow fade, but to a violent, absolute end for everything. They gave it a name that was as simple as it was horrifying: the Big Rip. To understand the sheer violence of this idea, you must first grasp the profound heresy at its core. The cosmological constant, that steady hum of energy in the vacuum, behaves in a predictable way. As a volume of space expands, the density of this energy remains perfectly constant. More space simply means more total energy, pushing everything apart at an ever-increasing but stable exponential rate. It's like a rising tide whose level never changes. The ocean just gets wider. Phantom energy, however, breaks this fundamental rule. It represents a form of dark energy with a kind of cosmic hunger, a positive feedback loop woven into the fabric of reality itself. For this phantom menace, expansion is not a consequence, it is fuel. As the universe expands, the density of phantom energy does not stay the same, it times increases asterisk. Think of it not as a tide, but as a fire that grows hotter the more it spreads, a sound that gets louder the farther it travels, feeding on the very emptiness it creates. This single terrifying property changes everything. It means the repulsive force of dark energy is not a constant pressure but a runaway reaction, an engine of annihilation that accelerates, faster and faster. The expansion of the universe stops being a smooth exponential curve and becomes a force with infinite potential. At first, this runaway expansion would be imperceptible, a subtle shift in the cosmic data, but the phantom is patient. It plays the longest of games, gathering strength in the expanding void over billions of years. While life evolves on planets and stars are born and die, this energy is quietly multiplying its pressure building, waiting for the moment when its outward push is no longer just a cosmic suggestion but an irresistible command. It begins a final chronological assault, a systematic dismantling of creation itself, working from the grandest scales down to the infinitesimally small. The Big Rip is not a singular event. It is a meticulously ordered execution. The first victims would be the great cosmic superstructures, the delicate web-like filaments of galaxy clusters that trace the largest patterns in the universe. Held together by the collective but tenuous pull of gravity over millions of light years, they would be the first to feel the strain. The growing repulsion of the phantom energy would begin to stretch these cosmic walls and voids, snapping the gravitational threads that connect them. Clusters that have been neighbors for 13 billion years would begin to accelerate away from each other at impossible speeds, their light redshifting beyond any hope of detection. The cosmic web, the very skeleton of the universe, would dissolve into an archipelago of isolated island universes, each one now adrift and utterly alone in a rapidly expanding sea of hostile space-time. For an observer inside one of these doomed realms, the rest of the cosmos would simply vanish. But the Phantom is not finished. It is merely clearing the board for its next move. Having isolated the galaxies, it turns its attention upon them. Our own Milky Way, a majestic gravitational gyroscope spinning for eons, is a delicate balance. The immense gravity of the supermassive black hole at its core, the combined pull of 400 billion stars, and the unseen halo of dark matter all conspire to hold it together against the inertia of its own rotation. For billions of years, this balance has held. Now, in the final stages of the universe, the ever-increasing push of phantom energy begins to overwhelm it. The process would be horrifically beautiful. The outer spiral arms, the stellar nurseries where new suns are born, would be the first to unspool, flung outwards like ribbons in a gale. The great river of stars flowing across our night sky, with thinnest stars, accelerating away from the galactic core, each one becoming a solitary point of light in the encroaching darkness. The gravitational heart of the galaxy, for so long the anchor of our cosmic home, would lose its grip. The Milky Way would be torn asunder, its billions of suns scattered into the void, a magnificent celestial city razed to its individual glittering bricks. The night sky would become a barren, empty canvas. And still the pressure builds. The countdown continues, but the timescale dramatically shortens. What took billions of years to tear apart galaxies now takes mere millions to obliterate solar systems. We think of our sun's gravity as an unbreakable bond, the force that has held our Earth in a stable, life-giving embrace for 4.5 billion years. Against the Phantom, it is nothing. In the last 60 million years before the end, this bond would begin to fail. The orbits of the outer planets Neptune and Uranus would grow erratic, their paths wobbling before they are finally cast off into the darkness, becoming rogue worlds on a final lonely journey. Then Jupiter, Saturn, Mars. Each planet in turn, our celestial family, would be ejected from the sun's embrace. Finally, it would be our turn. The Earth would be wrenched from its orbit, its connection to the sun severed forever. Our world would become a frozen rogue planet hurtling through an increasingly hostile void, a final witness to the dissolution of its own solar system. The sun itself would be just one more isolated star, its family of planets lost to the ever more violent expansion. Now the horror becomes immediate, the timescale collapsing from millions of years to mere minutes. In the last 90 minutes of existence, the phantom energy's repulsive force would have grown so powerful that it begins to challenge the gravity of planets themselves. For the Earth, the end would be apocalyptic. The force holding our world together would be overpowered. You would feel the ground beneath you cease to be a solid thing. Enormous chasms would rip open, not from tectonic stress, but because the fabric of space itself is pulling the planet apart. The atmosphere would be stripped away instantly, boiling off into the vacuum. The oceans would flash into vapor as the pressure dropped to nothing. Mountains would be torn from their roots and flung into space. The very core of our planet, the dense iron heart that generates our protective magnetic field, would be exposed and then shattered. The Earth, our home, the crucible of life, would disintegrate into a cloud of rapidly expanding rock and dust in the final minutes of cosmic time. The assault, however, has not yet reached its ultimate conclusion. The phantom energy has unmade every structure bound by gravity, but the fundamental nature of matter, held together by the electromagnetic and nuclear forces, remains intact. The final seconds of the universe are a battle against the very laws that make existence possible. With the expansion now accelerating at an almost unimaginable rate, the phantom's force becomes strong enough to overwhelm the electromagnetic bonds that hold atoms together in molecules, and molecules together in objects. Anything that remained a rock, a crystal, your own body, would be instantly atomized, its constituent parts scattered. You would not simply die, you would cease to be a coherent object. You would become a cloud of individual unbonded atoms, each one accelerating away from every other. The concept of things would be erased from the universe. But there is one final sacred bastion to conquer. In the last 0 to the -19 seconds, a sliver of time so small it is almost meaningless, the density of the phantom energy becomes nearly infinite. Its repulsive force now exceeds the strong nuclear force, the most powerful force in nature, the glue that binds protons and neutrons together inside the atomic nucleus. This is the unbreakable heart of reality, the force that forges elements in the cores of stars and has held the building blocks of matter together since the first moments after the Big Bang. And in this final infinitesimal fraction of a second, even this titan falls. The phantom energy rips atomic nuclei apart, shredding protons and neutrons into a quark gluon plasma, which is itself then torn into its fundamental constituent parts. Every atom in the universe, from the hydrogen in a distant star to the carbon in your cells, is simultaneously and catastrophically disintegrated. Matter in any form we could possibly recognize ceases to exist. This is the crescendo of the Big Rip. The universe is now an empty, featureless void, containing only elementary particles and photons, each one isolated and flying away from every other at superluminal speeds. There is nothing left to tear apart. Or is there? The theory's conclusion is the most mind-bending of all. As the final moment arrives, time equals zero, the scale factor of the universe and the density of the phantom energy both become infinite. The expansion rate is no longer just fast, it is infinitely fast. And at that moment, the very fabric of space-time, the stage upon which this entire cosmic drama has played out, is itself shredded. The concept of distance loses all meaning. The connection between cause and effect is severed. Time itself comes to an end. It is not a singularity of infinite density like a black hole or the Big Bang. It is a singularity of infinite scale, a cosmic null point, where every law of physics breaks down utterly and completely. Unlike the Big Freeze, there is no remnant, no frozen cinders, no slowly decaying black holes, no information preserved. There is only an absolute and final end, a state of universal non-existence from which no new beginning can ever emerge. It is a theory of ultimate annihilation, a vision of the cosmos that is not just ending but is being systematically, meticulously, and completely erased. This terrifying prediction, born from a single mathematical parameter, pushed beyond its limits, presents us with the most profound question of all. Is this just a chilling piece of theoretical speculation, a ghost in the machine of our cosmological models, or is there evidence, however faint, lurking in the dying light of the most distant stars that suggests this phantom is real and this horrifying countdown has already begun? The answer awaits us. Hidden in the darkness between the galaxies, a darkness that may be far more active and far more malevolent than we ever dared to imagine. To unmake a universe, you need more than just a simple push. You need something malevolent, a form of energy so strange, so paradoxical it seems to crawl out of a nightmare and into the equations of physics. You need a ghost in the cosmic machine, and physicists have given this phantom a name. They call it phantom energy. It is a concept born from the deepest anxieties of modern cosmology, a dark mirror to the energy we thought we were beginning to understand. For decades, we've grappled with dark energy as a cosmological constant, a placid, unchanging sea of energy inherent to space itself, its pressure remaining forever constant as the universe expands around it. This was Einstein's Lambda, a steady hand pushing the cosmos apart at an ever-accelerating yet predictable pace. In this future, galaxies would drift away into an eternal lonely night, a big freeze of unimaginable cold and darkness. A somber end, but a quiet one. Phantom energy, however, offers no such peace. It is not a constant, it is a contagion. Imagine a substance whose density does not decrease as space expands. Imagine instead that its density times increases asterisk. This is the chilling, defining characteristic of phantom energy. As the fabric of space-time stretches, the amount of this bizarre energy within each cubic centimeter of the void doesn't just stay the same, it grows. It's a runaway process, a positive feedback loop of cosmic proportions. More space creates more phantom energy, which in turn creates more space even faster, which then generates even more phantom energy. The expansion doesn't just accelerate, the acceleration itself accelerates. It is an exponential explosion of nothingness, a cancerous growth of the void. This idea is so deeply unsettling because it seems to break everything we know. It suggests energy can be created from literally nothing conjured, from the stretching of the vacuum in a blatant violation of the most sacred principles of energy conservation. It represents a universe that has lost all self-control, a system whose expansionary pressure is not a feature but a fever that will continue to rise unstoppably until it consumes the patient entirely. To grasp just how alien this concept is, we must journey into the foundational rules that govern reality, a set of principles known as the energy conditions. These aren't laws in the way that gravity is a law, but rather they are a set of common-sense guardrails for the cosmos, assumptions physicists make about the nature of matter and energy to prevent their theories from descending into utter chaos. One of the most fundamental is the null energy condition. It's a deceptively simple idea that for any observer traveling at the speed of light, the energy density they encounter will never be negative. It essentially dictates that gravity on the whole is always attractive. Matter and energy pull things together. They cause spacetime to curve inward. Even light with its zero rest mass bends spacetime, its path dictated by the gravitational wells carved by stars and galaxies. This principle is woven into the very fabric of general relativity. It is the bedrock upon which our understanding of black holes' gravitational lensing and the Big Bang itself is built. It ensures that the universe, for all its mysteries, behaves rationally. Phantom energy obliterates that rationality. It possesses a form of negative pressure so extreme, so potent, that it doesn't just counteract gravity, it violently reverses it. It represents gravitational insanity. Its presence forces the null energy condition to be violated, meaning an observer could, in theory, encounter a region of reality where the effective energy density is negative. This isn't just a simple push like the cosmological constant. This is an active, aggressive, and ever-increasing times repulsion asterisk. It is anti-gravity on an existential scale, a force that tells space-time not just to expand, but to tear itself asunder. The implications are staggering. The violation of this condition could theoretically allow for the existence of traversable wormholes, stable time machines, and other exotic phenomena long relegated to the fringes of science fiction. But in the context of the Big Rip, this violation has only one meaning. The gravitational glue that holds the universe together is destined to fail. The fundamental force that assembled galaxies, ignited stars, and formed planets will be overwhelmed by a repulsive foe that grows stronger with every passing moment. It is the ultimate cosmic betrayal. This is why the existence of phantom energy creates such a deep schism within the community of theoretical physics. For many, it is simply a bridge too far, a mathematical ghost story. They argue that such a substance cannot be physically real. They see it as a pathology in our theories, a sign that general relativity itself may be incomplete at these extreme energy scales. Perhaps our understanding of gravity needs a fundamental revision. Perhaps dark energy is not a new substance at all, but a manifestation of extra dimensions or a more complex quantum vacuum. To this camp, phantom energy is a warning sign from the cosmos, a message that our current models are breaking down and that we are missing a crucial piece of the puzzle. They find it philosophically abhorrent, an ugly and chaotic solution to the mystery of cosmic acceleration. Nature, they believe, should be more elegant. The ultimate fate of existence should not be scripted by such a monstrous entity. But another camp of physicists urges caution against such certainty. They are the pragmatists, the observers who argue that we must follow the data no matter where it leads, no matter how uncomfortable the destination. For them, our aesthetic preferences for how the universe times should times work are irrelevant. All that matters is how it does times work. And right now, the observational data, while uncertain, does not definitively rule phantom energy out. Our measurements of the expansion history of the universe, gleaned from the light of distant supernovae, and the subtle patterns in the cosmic microwave background all converge on that critical value, the equation of state parameter, *W*. If times W times equals exactly -1, we live in a universe with a cosmological constant headed for a placid big freeze. If times W times is greater than negative, one dark energy will weaken over time, and the universe might even collapse back on itself in a big crunch. But if times W times is less than -1, even by the smallest fraction, then we are living in a phantom universe. We are on a collision course with the Big Rip, And here we stand perched on a cosmic razor's edge. The challenge we face is one of almost unimaginable precision. We are trying to measure the fundamental nature of reality itself by observing the faintest flickers of light from the edge of the visible universe. It is an act of cosmic archaeology piecing together the story of our expansion from ancient photons that have traveled for billions of years to reach our telescopes. Each of these photons carries a tale of the stretching of space, its wavelength redshifted by the cosmic journey. By comparing the redshifts of countless standard candles like Type Ia supernovae, we can build a map of how the expansion rate has changed over cosmic time. From that map, we can attempt to calculate the value of times W asterisk, but our view is obscured by a fog of uncertainty. The distances are immense, the light is faint, and the sources are imperfect. Is that supernova slightly dimmer because it is farther away, or because its light was partially blocked by intergalactic dust? Are the patterns we see in the large-scale structure of galaxies a true reflection of dark energy's influence, or are they skewed by the complex physics of galaxy formation? Each measurement we make comes with an error bar, a zone of uncertainty, and for now the value of times W asterisk equals -1 sits comfortably inside those error bars. But so do values like -1.05 or -1.1. Our current instruments cannot tell the difference. We are like sailors on a dark sea trying to determine if the distant shore is a stable continent or the edge of a world-ending waterfall. From our current vantage point, they look identical. The difference between an eternity of cold emptiness and a finite violent end is hidden in the third decimal place of a single cosmological parameter. A number we are desperately trying to nail down using every technological and intellectual tool at our disposal. The stakes of this measurement are nothing less than the ultimate nature of time and existence, because the Big Rip isn't just an end, it is a singularity. We are familiar with the singularity of our past, the Big Bang, a moment of infinite density, infinite temperature, and infinite curvature, all contained within a point of zero volume. It was the beginning of space and time as we know it, the alpha point from which all of causality flows. The laws of physics break down at the Big Bang singularity because the quantities they are meant to describe become infinite. It is a wall in our past beyond which our current science cannot see. The Big Rip proposes an equal and opposite horror, a singularity in our future. But this one is profoundly different and in many ways more terrifying. It is not a singularity of compression but of expansion. It is not a point of infinite density but a moment of infinite timescale asterisk. The scale factor of the universe, its measure of size, will become infinite, and unlike the Big Bang, which happened at a single point, the Big Rip singularity happens everywhere at once. There is no place to hide, no escaping it. For every observer in every galaxy, the end arrives at the same cosmic instant. The fabric of space-time itself achieves an infinite rate of expansion. What does this mean for the laws of physics? It means they cease to exist. A physical law requires a physical universe in which to operate. It needs particles to govern, forces to mediate, and a stable space-time to exist within. In the final moment of the Big Rip, all of these things are gone. There are no particles, there are no forces, there is no structure. There is only an infinitely expanding void moving at infinite speed. The very concept of a law becomes meaningless. This future singularity raises a disturbing question about energy itself. The first law of thermodynamics, the conservation of energy, states that energy cannot be created or destroyed, only transformed. It is the most robust and tested principle in all of science. Yet the phantom energy driving the Big Rip seems to defy it outright, its density growing as if summoned from nothing. Does this mean the law is wrong, or does it mean that our definition of the universe is incomplete? Some theorists propose that the energy is being siphoned from another dimension, or that our universe is just one part of a larger multiverse, and that the total energy of the entire system remains constant. In this view, our universe dies, so that another may be born, our energy sacrificed, to fuel a cosmic process beyond our comprehension. But these are merely speculations, desperate attempts to find a rational explanation for a fate that seems to defy all reason. The truth is, we do not know. The Big Rip represents an ultimate boundary not just for matter and energy, but for knowledge itself. It is a future that consumes its own past, erasing every star, every planet, every atom, and every piece of information they ever contained. It is the final definitive act of cosmic censorship. If our universe is destined for this fate, then everything we have ever known or will ever know is temporary. Every discovery, every work of art, every memory, every life is written on a page that is destined to be torn from the book of existence. The universe would not just end, it would become a story that was never told. The implications are profound, forcing us to confront the possibility that the cosmos is not a stable eternal stage for our existence, but a fragile structure balanced on a knife's edge, capable of a violence so absolute it beggars the imagination. A violence we are now for the first time beginning to comprehend as we piece together the final terrifying moments of existence. And so the destiny of everything you have ever known, of every star and every world, comes down to this. It rests not on a prophecy or a myth, but on the cold, hard value of a single number, a ghost in the cosmic machine. An unknown quantity we label with a simple letter. This one variable in our equations of the universe acts as the ultimate cosmic switch, a fulcrum upon which all of future time is balanced. If W equals precisely -1, our cosmos is fated to a long, slow and lonely decay, an eternal silent expansion into the big freeze, a gentle fade to black. But if that number dares to dip even infinitesimally lower to -1.01 to -1.1, then the phantom is unleashed. The repulsive force of dark energy will grow, not just pushing galaxies apart, but eventually overwhelming every force that holds reality together. A future of unimaginable violence awaits a universal disintegration known as the Big Rip. The line between forever and the end is drawn at -1. But how? How do we, from our tiny perch on this spinning rock, measure the vital sign of the entire universe? How can we possibly hope to take the pulse of a force that is fundamentally invisible, a force whose only evidence is the accelerating retreat of everything from everything else we cannot touch? We cannot capture it in a lab. We can only witness its grand cosmic effects written in the language of light across billions of years. To read that language, to decipher that number, humanity has embarked on the most ambitious quest for knowledge in its history. We have become cosmic cartographers, building a new generation of eyes on the universe, technological marvels of unprecedented scale and sensitivity, all designed to hunt for the signature of our ultimate fate. This is the story of that hunt. It is a story of ingenuity, of persistence, and of our collective refusal to simply be passengers in the cosmos. We demand to read the final chapter. Our first great assault on this profound mystery began not in the vacuum of space, but high in the thin, crystalline air of the Chilean Andes. Here, perched atop a mountain named Cerro Tololo, sits a machine built for a single audacious purpose, the Dark Energy Survey. For 6 years, its powerful heart, the 570-megapixel Dark Energy Camera, or DCAM, one of the most formidable digital cameras ever constructed, stared into the southern sky. It did not hunt for singular, beautiful objects. Its goal was far grander. It conducted a celestial census, methodically mapping 1/8 of the entire sky night after patient night. It charted the precise locations, shapes, and distances of hundreds of millions of galaxies, creating a map of the universe of staggering scope and detail. The goal was not just to see the cosmos, but to understand its evolution, to watch the cosmic web of structure grow over 7 billion years of cosmic time. And within that monumental dataset, scientists would search for the subtle telltale fingerprints of dark energy's influence using 4 distinct and powerful techniques, each one a check and balance on the others. The first method is our most trusted and battle-tested tool, the Type IR supernova. These are the universe's standard candles, the spectacular death throes of a specific kind of star. They explode with a known, predictable, ferocious brightness, allowing us to use them as cosmic distance markers. By finding these explosions in the distant universe and measuring how faint and therefore how far they appear, we can chart the expansion history of space-time itself. They are our lighthouses in the cosmic storm, and the Dark Energy Survey meticulously catalogued thousands of them each, a vital data point revealing how fast the shores of reality were receding from us in different cosmic epochs. Their dimming light carries the story of the stretching void, but supernovae are only part of the puzzle. The second probe used by the survey is something far more subtle, a ghostly echo from the dawn of time. We call them baryon acoustic oscillations, or BAO. In the first few 100,000 years after the Big Bang, the universe was a hot, dense soup of plasma. Gravity tried to pull this plasma together, while the intense pressure of light fought back, creating colossal sound waves that rippled through the primordial cosmos. When the universe finally cooled enough to become transparent, these ripples were frozen in place, imprinted onto the very fabric of reality. They left behind a faint preference for galaxies to form at a specific distance from each other, about 500 million light-years. This cosmic echo provides us with a gigantic pre-measured standard ruler. By identifying this pattern in the distribution of the hundreds of millions of galaxies mapped by the Dark Energy Survey, astronomers can measure the geometry of space and how that geometry has been stretched by cosmic expansion over the galaxies, eons. It is like finding a yardstick of a known length left behind by the Big Bang that we can now use to measure the universe's changing dimensions. The third technique is perhaps the most elegant, relying on Einstein's own theory of relativity. It is called weak gravitational lensing. We know that massive objects, like galaxies and great clusters of galaxies, warp the space-time around them. Light from more distant objects travelling to us across billions of years must pass through this lumpy, distorted cosmic web. Its path is slightly bent, its image infinitesimally sheared and magnified. The effect on any single galaxy is impossibly small and undetectable. But by analysing the shapes of hundreds of millions of galaxies, the Dark Energy Survey could tease out a statistically significant pattern of these subtle distortions. This allows us to create a map not just of the visible matter but of all matter, including the vast invisible scaffolding of dark matter. Dark energy, by accelerating expansion, actively fights against the gravitational pull of this matter, slowing down the rate at which these cosmic structures can grow. By mapping the history of this cosmic tug-of-war between gravity's embrace and dark energy's relentless push, we get another powerful measurement of its properties. Finally, the survey turned its gaze to the grandest structures in the cosmos galaxy clusters. These are the great metropolises of the universe, gravitationally bound empires containing hundreds or even thousands of galaxies. They are the most massive objects held together by gravity, and their very existence is a sensitive barometer for dark energy's influence. In a universe dominated by gravity, these clusters should grow more and more massive over time. But in a universe with a strong dose of dark energy, the accelerating expansion acts as a cosmic brake, stifling their growth by making it harder for gravity to pull in more material from the ever-widening void. By counting how many of these colossal clusters exist at different distances, and thus at different times in cosmic history, the Dark Energy Survey could once again probe the strength of dark energy's repulsive force. After years of painstaking observation and mind-bendingly complex analysis, the verdict from the Dark Energy Survey came in. With unprecedented precision using all four methods combined, the team measured the value of W. Their result was astonishing. It was -1 with an uncertainty of just a few percent. The number was perfectly consistent with Einstein's cosmological constant. The data pointed not to a violent big rip, but to the slow, quiet, inexorable big freeze. A sigh of relief perhaps for the distant fate of the universe. But in science, consistency is not proof. The key is the uncertainty, that nagging margin of error. Within that small window of doubt, the phantom could still be lurking. The measurement was breathtakingly precise, the best of its kind ever achieved from the ground, but it was not yet definitive. To truly corner our cosmic ghost, to shrink those error bars into submission, and stare our fate in the face, we knew we had to go beyond the blurring interference of Earth's atmosphere. We had to go to space. This is where the next chapter of our quest begins, with a machine that is a testament to global scientific collaboration. It is called Euclid, a mission of the European Space Agency with crucial contributions from NASA. Launched in 2023, Euclid is now orbiting the Sun 1 million miles from Earth at a gravitationally stable point in space, known as the second Lagrange point, or L2. From this cold, dark, and silent vantage point, free from the distortions of our planet's atmosphere, Euclid is embarking on a survey that will dwarf even the mighty achievements of the Dark Energy Survey. Over 6 years, it will map more than a third of the entire sky, creating the largest and most accurate 3D map of the universe ever made. Its gaze will pierce 10 billion years into the past, covering the entire epoch when dark energy began its hostile takeover of the cosmos. Euclid is equipped with 2 extraordinary instruments, 2 eyes that see the universe in different ways. Its visible light instrument VIS will measure the shapes of billions of galaxies with a sharpness that can only be achieved from space. It is a weak lensing machine of unparalleled power, designed to map the subtle distortions caused by the cosmic web with exquisite precision. This will allow it to trace the growth of cosmic structure over time, providing one of the most sensitive probes of dark energy's behavior we have ever conceived. At the same time, its near-infrared spectrometer and photometer NISP will do something different. It will measure the precise distances to tens of millions of galaxies, adding the crucial third-dimension depth to our map of the cosmos. This allows it to hunt for those baryon acoustic oscillations, our cosmic ruler, with stunning accuracy across vast cosmic volumes. By combining these 2 primary techniques, weak lensing and BAO, Euclid isn't just taking a picture. It's performing a cosmic tomography scan. It is reconstructing the geometry of the dark universe layer by layer, epoch by epoch, watching how the cosmic push and pull has evolved over 10 billion years. Its data will refine our measurement of W by another order of magnitude, potentially shrinking the window of uncertainty so dramatically that the phantom has nowhere left to hide. It could be the mission that finally tells us if O is truly eternally locked at -1. Yet even Euclid is not the final word. The human drive to know to be certain has pushed us to build an even more powerful tool, a machine that represents the next great leap in our observational capabilities. Sometime in the near future, we will launch what is arguably the most ambitious dark energy hunter ever devised, the Nancy Grace Roman Space Telescope. Roman is a revolutionary concept. While its mirror is the same size as the Hubble Space Telescopes, its vision is breathtakingly wider. Its camera will have a field of view 100 times larger than Hubble's. Where Hubble provides a keyhole peek into the universe, Roman will throw open the grand bay windows, capturing vast cosmic landscapes in a single observation with Hubble-like clarity. This immense field of view will fundamentally change the game. Roman will conduct a high-latitude survey that images a patch of sky thousands of times larger than any deep field Hubble has ever taken. In doing so, it will measure the shapes and distances of billions of galaxies, creating a weak lensing and BAO map of such scale and depth that it will push our cosmological models to their absolute breaking point. But perhaps Roman's greatest strength in this specific quest will be its power as a supernova hunter. Because of its wide, sensitive gaze, Roman will be able to perform a supernova survey of unprecedented scale. Instead of finding them by the dozens or hundreds, it will discover and track thousands upon thousands of Type Ia supernovae in the distant universe. This sheer statistical power will allow us to chart the universe's expansion history with a smoothness and fidelity that was once the stuff of science fiction. Every new supernova is another pin on the map, another dot on the graph that traces the expansion of reality. With Roman's data, that line will be drawn with a fine-tipped pen, not a thick marker. The subtle deviations, the tiny changes in the rate of acceleration over time, will be revealed. This is the crucial test. If dark energy is a simple cosmological constant, its effect should be, as its name implies, constant. But if it is something more dynamic, something that changes its strength over time, as a phantom energy field might do, Roman's supernova survey is our best hope of catching it in the act. And this grand observational assault is not limited to these flagship space missions. Back on Earth, an even larger eye is preparing to open. In Chile, the Vera C. Rubin Observatory is nearing completion, its gargantuan 8. A 4-meter mirror and 3200 megapixel camera will survey the entire southern sky every few nights, generating an ocean of data on a scale humanity has never before dealt with. Its legacy survey of space and time will provide another independent treasure trove of data on weak-lensing BAO galaxy clusters and supernovae, complementing and cross-checking the results from space. This is a global endeavor, a multi-pronged attack on a single fundamental mystery. We are throwing the full force of human intellect and technological prowess at this one question, deploying our greatest observatories on the ground and in space. They are our proxies in the ultimate detective story, our eyes and ears across the void. Each mission from DES to Euclid to Roman is designed to peel back another layer of the unknown, to refine the measurement, to tighten the constraints, to corner the truth. All this metal, all this glass, all these decades of human effort, from the minds who first conceived these missions to the engineers who painstakingly built them and the scientists who now analyze their data, it all comes down to a number. Every galaxy catalogued, every supernova flash recorded, every subtle distortion of light measured, it is all being fed into our cosmic models designed to do one thing, to calculate the value of one with enough precision to be certain. The error bars are shrinking. With each new data release, the realm of possibility narrows, and the true nature of our universe's destiny comes into sharper focus. We are standing on a precipice of discovery closer than any generation before us to answering the most profound question we can ask about our future. Are we living in a universe that will simply expand forever into a cold and empty darkness? Or are we unknowingly passengers on a runaway train accelerating toward a final violent moment when the very fabric of space-time will be torn? Asunder, the evidence is coming in. The answer is waiting for us, hidden in the light from a billion distant galaxies. And so we stand at the edge of that ultimate abyss, our minds reeling from the sheer, unbridled violence of the proposition. We have journeyed across billions of light years, peering back into the dawn of time itself, only to arrive at this terrifying precipice. To witness in the cold, unblinking equations of our own, devising the theoretical blueprint for the obliteration of everything. The Big Rip is not merely an end, it is an unraveling, a cosmic annulment, where the very laws that bind matter and energy are rendered impotent by a force that should not exist. From the simple, elegant puzzle of why distant supernovae appeared dimmer than expected, we have followed a breadcrumb trail of dying stars across the expanding void. That faint, perplexing light, a whispering secret carried on the cosmic winds for over 7 billion years, became the key that unlocked a new and unsettling chapter in the story of the universe. What began as a mission to measure the past, to chart the history of cosmic expansion with unprecedented precision, inadvertently became a harrowing prophecy of the future. The data, when it first arrived, was so counterintuitive, so profoundly at odds with a century of cosmological thought, that it was initially dismissed as error. A universe slowing down, gracefully succumbing to the eternal pull of its own gravity, was the accepted narrative, the expected outcome of the Big Bang's primordial fury. But the evidence refused to yield. The standard candles were not lying. The universe was not slowing down. It was accelerating. An unknown energy, a pervasive, untouchable presence woven into the very fabric of space-time, was pushing everything apart, acting as a form of cosmic anti-gravity. We gave it a name as mysterious as its nature: dark energy. This single discovery, born from the meticulous observation of stellar explosions in galaxies unimaginably remote, reshaped the entire landscape of physics. It was as if we had spent millennia mapping a vast continent only to discover that our maps depicted a mere 5% of its actual landmass, with the rest shrouded in an impenetrable unknown territory. This journey has forced us to confront the deepest of cosmic ironies, that the force which may ultimately tear every atom asunder is not a cataclysm of fire and density, but the quiet, relentless pressure of nothingness itself. The vacuum of space, once considered a passive stage upon which the grand drama of matter unfolded, revealed itself to be the story's most powerful and enigmatic actor. It possesses an intrinsic energy, a repulsive force that grows stronger as space itself expands, creating a terrifying feedback loop. More space means more dark energy, which in turn creates more space faster and faster in an exponential runaway cascade. From that revelation, the Big Rip hypothesis emerged not from wild speculation, but as a direct, logical, and deeply disturbing consequence of our own observations. If this phantom energy, this strange property of the void, were to grow just slightly more potent over cosmic time, the future would be sealed. The acceleration would become infinite. The final act would be written not in fire, but in dissolution. And yet, for all its terrifying elegance, the Big Rip is not a predetermined fate. It is a possibility, a dark shadow cast by our current ignorance. You must understand that science does not operate on certainty, but on the careful weighing of evidence. The future of the cosmos, as we currently understand it, is not a single unchangeable path, but a branching road with several potential destinations, each one defined by the precise character of the dark energy that dominates our universe. The value we call omega, the equation of state parameter, that acts as the universe's ultimate control knob, is the fulcrum upon which all of existence pivots. If its value is precisely -1, as the cosmological constant Albert Einstein once proposed, then our universe is destined for a far quieter, more melancholic end, an eternity known as the Big Freeze, or the heat death. In this scenario, the acceleration continues, but it is a steady, constant push. The galaxies will be driven apart one by one, their light receding beyond our cosmic horizon, until our own galactic island, the local group, is all that remains in an otherwise empty, observable universe. The sky you see now ablaze with the light of 100 billion galaxies will become a black, featureless void for our distant descendants, should any exist. The era of star formation will eventually end as the universe runs out of free gas. The stars themselves will burn out, leaving behind a graveyard of black dwarfs, neutron stars, and solitary black holes. Over unimaginable timescales, even these remnants will decay their constituent protons, dissolving into whispers of radiation. The universe will become a thin, cold, and utterly dark soup of elementary particles growing ever more dilute, approaching a state of maximum entropy from which no work, no life, no complexity can ever again arise. It is an end of profound loneliness, a slow, inexorable fading into eternal twilight. This cold death is for many cosmologists the most likely outcome, a future consistent with our most precise measurements of dark energy so far. But those measurements still carry a sliver of uncertainty, a tiny margin of error, and within that sliver, within that razor-thin window of possibility, lies the more violent potential of the Big Rip. If omega is even fractionally more negative than -1, we enter the realm of phantom energy. This is the runaway engine, the accelerating acceleration that leads to a finite end. So we are left on a cosmic knife edge, balanced between two profound expressions of oblivion, the slow, lonely chill of the Big Freeze and the swift, violent disintegration of the Big Rip. There is, of course, a third, more classical option, now largely considered unlikely, due to our observations of acceleration, the Big Crunch. In this scenario, if dark energy were to weaken or even reverse its polarity, gravity would eventually regain its throne. The expansion would slow, halt, and then reverse. Galaxies would rush back towards each other, their blue-shifted light a harbinger of the coming conflagration. The universe would collapse back into an infinitely hot, infinitely dense singularity, a mirror image of the Big Bang, perhaps even seeding the birth of a new cosmos in an eternal cycle of creation and destruction. But the evidence as it stands today points away from this fiery rebirth. It points outwards towards an eternity of expansion. Our destiny appears to be written in cold and darkness, the only real question being whether it will be a gradual fade or a sudden catastrophic tear. But to focus solely on the final terrifying paragraph of the cosmic story is to miss the true significance of our discovery. The most profound revelation of this entire journey is not how the universe might end, but how little we truly know about it right now. The discovery of dark energy was a Copernican-scale revolution, a moment of intellectual humility that shattered our comfortable gravity-dominated view of the cosmos. For centuries, we believed we understood the primary forces at play. We had gravity, the grand architect of structure, the celestial shepherd that corralled gas into stars and stars into the majestic spiral arms of galaxies. And we had the Big Bang, the initial impulse, the explosive origin, whose momentum gravity was steadily, patiently working to overcome. It was a beautiful Newtonian clockwork, a grand cosmic ballet choreographed by a single, well-understood force. Dark energy tore that picture to shreds. It introduced a ghost into the machine, an invisible, untouchable entity that accounts for nearly 70% of the total energy density of the universe. Imagine for a moment the sheer scale of that admission. We, a species that has split the atom, decoded the genome, and sent robotic emissaries to the edge of the solar system, have only just realized that the dominant component of our own universe is a complete and utter mystery. We do not know what it is. We do not know where it comes from. We know it only by its effect, the subtle but inexorable push it exerts on the fabric of space-time. Is it a fundamental property of the vacuum, as Einstein's constant suggests, a new undiscovered field permeating all of space, a kind of cosmic quintessence? Or is it a sign that our theory of gravity, general relativity, is incomplete breaking, down on the very largest of cosmic scales? Each possibility is as revolutionary as the last. Each one sends physicists back to their blackboards, forcing them to re-evaluate the very foundations of their science. This is the true legacy of the search that led us to the Big Rip. Dark energy has transformed cosmology from a science of charting what is known into a science of exploring what is unknown. It has opened up a chasm in our understanding, a void teeming with questions that will drive scientific inquiry for generations. It forces us to confront the possibility that the universe is fundamentally stranger, more complex, and perhaps more hostile to structure and life than we ever dared to imagine. The four forces we have meticulously catalogued, gravity, electromagnetism, and the strong and weak nuclear forces, the very pillars of our standard model of particle physics, now appear as mere actors on a stage whose size, shape, and ultimate fate are dictated by a force we have yet to name or comprehend. We are like ancient mariners who have just realized that their world is not a flat plane but a sphere, and that the familiar currents they have charted are governed by the unseen global rotation of the entire planet. The existence of dark energy, and by extension dark matter, tells us that we are living in a universe where the visible is but a tiny froth on the surface of a deep, dark, and invisible ocean. That realization is at once terrifying and exhilarating. It is a call to adventure, a promise that the greatest discoveries about the nature of reality still lie ahead of us, waiting to be found in the subtle stretching of space-time and the fading light of distant exploding stars. And so we find ourselves here in the 21st century, armed with telescopes of unprecedented power and theories of breathtaking scope, yet humbled by the magnitude of the mystery before us. We look out at the cosmos, not with the arrogance of a species that has solved it all, but with the wide-eyed wonder of a child just beginning to ask the right questions. We have built these magnificent instruments, these cathedrals of science like the James Webb Space Telescope and the Vera Rubin Observatory, for this exact purpose, to stare into the darkness and seek answers. These are not mere tools, they are extensions of our own innate, unquenchable curiosity. They are the latest expression of an impulse that is as old as our species itself, the same impulse that drove our ancestors to watch the clockwork procession of the planets and to chart the changing of the seasons in stone. The same drive that led Galileo to turn his newly crafted telescope towards the heavens, shattering the crystalline spheres of antiquity and revealing a universe far larger and more dynamic than anyone had ever dreamed. We look because we must. It is encoded in our DNA. We are the universe's attempt to understand itself. Our brief, ephemeral consciousness, born on this tiny, fragile world, has somehow developed the capacity to look back and piece together the story of its own origin and to contemplate its ultimate end. That is the true miracle. Not that the universe exists, but that we exist within it, capable of comprehending, even in a limited way, its grandeur and its terror. Whether our cosmos is destined to be ripped apart to freeze into a silent oblivion, or to collapse into a fiery singularity, the outcome does not diminish the profound nobility of our quest. The pursuit of this knowledge, the simple act of looking up and asking, why, is perhaps the most meaningful thing we can do. It is our covenant with the cosmos, our promise to bear witness to its majesty for as long as we are able. The final fate of all things may lie trillions of years in the future, a reality so remote as to be almost imaginary. But the questions it raises are here with us now. They fuel our science, inspire our art, and define our place in the grand tapestry of existence. The mystery of dark energy reminds us that we are still at the very beginning of our journey of discovery. And that, even in the face of an accelerating void and the terrifying potential for a final violent end, in the light of human curiosity, our relentless search for understanding remains the most powerful and enduring force we know.